Welcome to the Henstitute. Today we are going to be talking about a magnetic field created by a current carrying wire. A scientist back in the 1800s by the name of Hans Christian Ørsted noticed in 1820 that when you had a wire that had a current flowing through it, so this example we have current flowing through this wire, that it would actually affect the compass needles of a compass nearby. Now, what he didn't realize is the direction of it, and that's what took him a long time to truly figure it out, because it's not actually in the parallel to the actual current, it's actually perpendicular to the current. And guess what? We're going to learn a new right-hand rule. There's a new right-hand rule right here. This is right-hand rule number 2. Rule number 2. And I tried to grab this picture from the book. The idea of the right-hand rule to figure out the direction of the current when you have or the direction of the magnetic field, when you have a current flowing through a wire, you actually take the fingers of your right hand and curl them around your current with your thumb pointed in the direction of the current. So notice that the thumb is pointed straight up, which is the same direction as our current here. Our current through this wire is pointed straight upward. So this is our current. This is the direction of our thumb, and the magnetic field here is actually going to point in the direction of our fingers that are curled around. So the magnetic field is actually going around this wire in a circle. So that's kind of weird. It's not in an actual direct line. It's actually going in circles. So I like this picture up here. These are representing our magnetic field. If you notice, we've got little arrows. One's pointing this way, and then it's pointing downward, and then it's pointing this way, and then upward. So the direction of the magnetic field is actually going around in a circle. So the magnetic field, B, remember magnetic field is B, is circular around the wire. That's one of the things that's kind of weird about it. It doesn't actually have a beginning and end. It's actually curving around. So the idea is you take your right hand, you point your thumb in the direction of the current, and your fingers will curl around that current to give you the direction of the magnetic field. Now, this gives us a brand new equation to actually find the magnitude of this magnetic field. So the magnitude of the magnetic field, which is going to be B, is going to be equal. It's actually directly dependent on the current. So in other words, if you have more current, you're going to have a larger magnetic field. So there's a direct relationship. I'm going to write this down here, that the magnetic field increases when your current increases. So a nice direct relationship between these two. The next thing it's going to depend on is actually how far away from the wire you are. So they've only drawn it so that we have one small little radius out here. Actually, I'm going to change that to a different direction so that we have just a small little radius. But if I was farther away from this, what I would notice is that there would actually be a series of circles going around our current. They would all be going in the same direction. They'd all be going in a clockwise direction in this particular case. But as we get farther away, we'd actually get a smaller magnetic field. So the magnetic field will actually decrease as the radius is increasing. So that's an inverse relationship. So that means I'm going to put my radius on the bottom. But since these are circles, what kind of displacement are we talking about with a circle? We're talking about a circumference. So actually on the bottom, it's not just r, it's actually 2 pi r. So we're actually dealing with the entire circumference on the bottom. The last thing is this is not actually going to give us the correct units for everything. So the last thing we need on here is some constant proportionality. The constant proportionality looks like this. It's the Greek letter mu. We've had that before with a little 0 on the end. So mu 0 is a thing called the permeability of free space. It's just a constant. We have had the permittivity, which was our little epsilon 0. So if you remember, we had epsilon 0 once before, which was equal to 8.85 times 10 to the negative 12. This was the permittivity of free space. This is now the permeability of free space, and it has a different value. Mu 0 is actually equal to 4 pi. So it's 4 pi, it's just that number, times 10 to the negative 7th power. It does have a unit. It's in Teslas times meters over amps. Really, all that's designed to do is make sure that everything cancels out. So we get our Teslas for our magnetic field. So you should see the meters would cancel out here, and our amps are going to cancel out. So we get everything to kind of work out. So this is going to be our one equation, but we also have a brand new right-hand rule for a magnetic field created by a current. And thanks to Hans Christian Ørsted here, because he's the first one that noticed this effect. Thank you.